Have you ever wondered why London, despite its northern latitude, experiences milder winters compared to cities like Calgary, which sit at a similar latitude? It's a question that highlights the intricate workings of our planet's climate system. The answer lies in a powerful oceanic force, the Gulf Stream. This is a massive, warm ocean current, a veritable river of heat flowing through the Atlantic. It acts like a central heating system for the entire northern hemisphere, distributing warmth and influencing weather patterns across continents. For centuries, this current has been a major player, shaping weather patterns, dictating temperatures, and influencing rainfall across vast regions. It has also supported diverse and thriving ecosystems, providing the conditions necessary for a rich tapestry of marine life to flourish. Indeed, the Gulf Stream has played a crucial role in making much of our world habitable, allowing for agriculture, settlement, and the development of civilizations. But now, scientists are sounding the alarm. They warn that the Gulf Stream, and the larger system it's part of, the Atlantic Meridional Overturning Circulation, or AMOC, a complex network of currents spanning the Atlantic, may be weakening to levels not seen in over 1,000 years. This slowdown is not just a minor fluctuation, it represents a significant shift in the ocean's dynamics. This isn't just a minor blip, it's a potential tipping point with far-reaching consequences. A slowdown of the AMOC could trigger global changes, impacting weather patterns, ocean temperatures, and even sea levels across the globe. These changes range from weather to food supplies, threatening the stability of ecosystems and human societies alike. The Gulf Stream, as we mentioned, is just one part of the AMOC, a key component in this larger system. The AMOC is a vast oceanic network that plays a critical role in regulating our climate and maintaining a delicate balance in the Earth's energy budget. In this video, we'll break down exactly what the AMOC is, exploring its intricate mechanisms and how it functions as a global conveyor belt. We'll also delve into why it matters, examining the critical role it plays in maintaining a stable and predictable climate. We'll explore what the latest science says about the AMOC's current state, drawing on cutting-edge research and expert analysis. Finally, we'll consider what a slowdown could mean for our future, exploring the potential consequences for weather patterns, sea levels, and global ecosystems. So, let's dive in and look at why this hidden river in the ocean, and the larger system it's a part of, deserves our immediate attention, right now. To understand the growing concerns surrounding our climate, let's start by taking a closer look at the Gulf Stream. This powerful current plays a vital role in regulating temperatures and weather patterns across the Atlantic. The Gulf Stream can be visualized as a fast-moving warm river flowing through the ocean. It's a concentrated stream of warm water, distinct from the surrounding cooler waters. This remarkable current originates in the warm waters of the Gulf of Mexico and the Caribbean Sea, gathering heat as it travels. From there, it flows northward, tracing the outline of the U.S. East Coast, acting as a warm bath along the eastern seaboard. As the Gulf Stream journeys north, it releases a significant amount of heat into the atmosphere through evaporation and direct transfer. This heat release is crucial. This process of heat release plays a critical role in warming the climate of Europe, especially Western Europe, making it significantly milder than other regions at similar latitudes. Without it, Europe would experience much colder winters. However, the Gulf Stream is just the visible surface expression of a much larger and more complex system known as the Atlantic Meridional Overturning Circulation, or AMOC. The AMOC is often described as a giant continuous conveyor belt operating within the Atlantic Ocean. This conveyor belt works by moving warm, relatively less dense water northward along the surface. Simultaneously, it transports cold, dense water southward at great depths. This deep southward flow occurs far below the ocean's surface, hidden from view. This continuous cycle of water movement is what allows the AMOC to circulate water. It also plays a crucial role in the global distribution of heat, and it distributes vital nutrients throughout the ocean ecosystem. Ultimately, the AMOC is a key component in regulating Earth's overall climate system. The primary engine driving this entire system is the sinking of cold, salty water in the North Atlantic. This sinking mainly occurs in the waters surrounding Greenland, and also near Iceland, where the water becomes dense enough to plunge to the ocean depths. The AMOC is an incredibly powerful force, moving more energy than all of humanity uses combined. This makes it a truly planetary-scale climate engine, influencing weather patterns and temperatures across the globe. The relative stability of the AMOC over centuries has allowed for the development of predictable weather patterns in North America, and also in Europe, contributing to the climate stability that has shaped societies and ecosystems. But the critical question is, what happens if this vital climate engine begins to sputter and weaken? What are the potential consequences? That's precisely the question that climate scientists and oceanographers are urgently investigating, as the stability of the AMOC is now being called into question. For years, climate models have consistently predicted that the Atlantic Meridional Overturning Circulation, or AMOC, could weaken significantly due to climate change. These models, complex simulations of the Earth's climate system, suggested a potential slowdown, but confirming these predictions with real-world data has been a significant challenge. The difficulty lay in gathering enough robust, long-term observational data to validate the model's projections. Direct measurements of ocean currents and temperatures are sparse and challenging to obtain, making it hard to detect subtle shifts in the AMOC's behavior. But real-world evidence was elusive, until now. A persistent and unusually cold patch of water located south of Greenland has emerged as a key indicator. This region, typically influenced by the warm waters transported northward by the AMOC, is now exhibiting anomalously low temperatures. This area of frigid water has been nicknamed the cold blob, and its presence is raising serious concerns among climate scientists. The cold blob has become increasingly prominent, appearing as a distinct feature on climate maps and ocean temperature visualizations. Its consistent presence signals a significant disruption in the expected temperature patterns of the North Atlantic. In a warming world characterized by rising global temperatures and melting ice caps, the existence of such a large and persistent cold anomaly is particularly striking. This cold spot is a glaring anomaly, standing in stark contrast to the overall trend of ocean warming observed across the globe. It highlights the complex and sometimes counterintuitive ways in which climate change can manifest. The presence of the cold blob suggests that less warm water is being transported to the region by the AMOC, disrupting the normal heat distribution patterns in the North Atlantic. It's a sign that the AMOC's crucial role in delivering heat from the tropics to the North Atlantic is faltering, potentially leading to significant regional and global climate consequences. Sediment cores extracted from the ocean floor and ice core data obtained from Greenland provide valuable historical context. These paleoclimate records reveal that the AMOC is now operating at its weakest level in at least 1,600 years, based on the analysis of various climate proxies. Furthermore, the data indicates that the slowdown of the AMOC has been accelerating since the mid-20th century, coinciding with the period of rapid industrialization and increased greenhouse gas emissions. The cold blob serves as a real-time fingerprint, a tangible manifestation of this weakening AMOC, providing a clear and present signal of a system in distress. This evidence is compelling, shifting the scientific conversation from theoretical possibilities to direct observation of a major climate system undergoing significant change. We're witnessing the effects of a weakening AMOC right now. The changes are no longer confined to future projections. The impacts are not something to be concerned about in some distant future. They are unfolding in real time, impacting weather patterns and ocean ecosystems today. The cold blob is the ocean's stark and undeniable warning, a clear signal that something fundamental is shifting. It's a warning that a key part of our planet's climate machinery, the AMOC, is undergoing a significant and potentially irreversible change, demanding immediate attention and action. The AMOC is more than an ocean current. It's a climate cornerstone. It keeps Europe's winters mild. Without it, the UK and Scandinavia would be as cold as northern Canada. The AMOC also stabilizes the jet stream, shaping weather across North America and Europe, and influences rainfall as far as Africa and South America. It oxygenates the deep ocean and brings nutrients to the surface, supporting marine life and fisheries. A slowdown could disrupt these cycles, starving the deep ocean of oxygen and nutrients. The AMOC moderates global temperatures, preventing extremes. Our stable climate, ecosystems, and societies depend on its steady churn. Its weakening is a threat not just to science but to the stability of nations. If the AMOC weakens or collapses, Europe faces dramatic consequences. Winters could drop by 5-15 degrees Celsius, plunging London and Paris into deep freezes more like Moscow or Siberia. Infrastructure built for mild climates would fail, pipes would burst, power grids would strain, and transport would grind to a halt. Storms would intensify, and agriculture would suffer as growing seasons shrink and staple crops fail. Food shortages and economic disruption would follow, with industries from farming to tourism collapsing. Energy costs would soar, and governments would scramble to adapt. The lush landscapes of Western Europe could become harsh and unrecognizable. This isn't just a cooler Europe, it's a continent in crisis, all because of a hidden ocean current. The AMOC engine relies on cold, salty water sinking in the North Atlantic. But melting Greenland ice and increased rainfall, both driven by climate change, are flooding the region with fresh water. Fresh water is less dense, so it forms a layer that won't sink, smothering the AMOC's engine. This creates a feedback loop. As the AMOC weakens, regional weather patterns shift, sometimes accelerating Arctic warming. The chain as clear-burning fossil fuels warms the planet, melts ice, adds fresh water, and weakens the AMOC. We're conducting a dangerous experiment with a system that's kept our climate stable for millennia. The cause and effect lead directly back to human activity. The AMOC's fate is in our hands. The 2004 movie, The Day After Tomorrow, imagined the AMOC's collapse as an instant global disaster. While the film's premise, fresh water halting the current and triggering a deep freeze, reflects real scientific concerns, its timeline is pure fiction. In reality, a collapse would unfold over years or decades, not days. There'd be no instant ice age or superstorms, but a gradual grinding shift, colder winters, stormier winters, and rising seas. The movie got people talking about climate tipping points, but the real science is sobering enough. A weakened AMOC would bring severe, long-term changes, not Hollywood-style apocalypse. The threat is real, but it's not a sudden spectacle. It's a slow-motion crisis. Understanding the difference matters for how we respond. The AMOC's collapse wouldn't just chill Europe, it would disrupt the entire planet. Tropical rain belts would shift, causing droughts in Africa's Sahel and weakening Asian monsoons, threatening food and water for billions. Some regions, like Brazil, could see catastrophic flooding. Sea levels along the U.S. East Coast could rise by up to a meter, flooding cities like New York and Miami. These changes would force millions to migrate, creating climate refugees and straining global resources. Food baskets could turn to dust and coastal communities could vanish. The AMOC's collapse is a story of global security, not just climate. Its ripple effects would reshape the world as we know it. So, what's the real outlook? A total AMOC collapse this century is unlikely, but a continued weakening is expected, and the risk is rising. We'll see colder European winters, stronger storms, and higher U.S. East Coast sea levels, even without a full shutdown. The tipping point could be closer than we think, possibly within decades. This uncertainty demands caution, not complacency. The main driver is fresh water from melting ice caused by global warming. The solution: cut greenhouse gas emissions, transition to clean energy, and protect forests to slow warming and stabilize the AMOC. Our civilization depends on a stable climate, and the AMOC is a linchpin. The science is clear. Act now, or risk